Video 6 for the light unit. Let's talk about spreading light, diffraction. We've talked about this before, but let's go back and revisit this. So when making powerful telescopes and microscopes, the wave nature of light becomes important again. Any wave, when passing through an opening, tends to spread out when it emerges on the other side. We call this diffraction. So there's a formula for this. The spread in the light equals the wavelength of the light divided by the diameter of the opening times how far away we're looking at it. So that's our wavelength right there. That's our D. And if I want to take a look at how far this spreads, and that'd be my value for R. Now, if we think about it then, all telescopes, all microscopes, even your eye works like this. So, if this is a telescope, here's the light waves coming in. They're going to diffract when they enter the telescope. And that's the same for microscopes and even your eye. So what that can do, it can cause some blurriness, if you will. So we have a similar equation to determine the closest objects that an optical system, such as a camera, your eye, a telescope, or microscope, the closest that an optical system can distinguish. And that distance is what we call resolution. So the formula for resolution, and this becomes very important. So this formula for resolution then, I'm going to give it a new letter. I'm going to call it B. It's actually kind of the same formula. Instead of calling it spread, we call it kind of like the resolution. So B then, our resolution, is going to be the separation of the objects. So think about it this way. Can you tell that there's two objects, or do they look like one object? How easily can we separate those objects when we view them through the viewfinder? So D now is going to be the size of the lens or the size of the opening. And then R is going to be the distance to the object. So let's work out an example for the human eye. So for the human eye, it has an opening of 5 millimeters. And the wavelength of light is approximately 5 microns. So then the resolution is going to be that right there. So B will equal 5 microns, or 0.5 microns. And then so I find that the resolution is 10 to the negative fourth times R, or I can say that this B over R equals 10 to the negative fourth. So this kind of gives us like our resolution to range ratio. So using that ratio, we can make some calculations about the farthest distance that we can see. Okay, the last topic I want to talk about is polarization. Light is a transverse electromagnetic wave. So what that means then is that the direction of the electric field is perpendicular to the direction that the wave is moving. Kind of like how you're shaking a rope is perpendicular to the direction of the wave along that rope. Electromagnetic waves, just like rope waves, are polarized. So what that means to be polarized is that if the wave shakes up and down relative to the wave motion, we say that it is vertically polarized. If I were to shake the rope left to right, we would say it's horizontally polarized. So I can think of light as being either vertically polarized, horizontally polarized, or any angle between the two. So the ordinary light from a light bulb or the sun consists of many waves that have many orientations, anywhere from vertical to horizontal. We call this unpolarized light. So here we have an example of unpolarized light. So some of the light is vertically polarized, some of it's horizontally polarized, and any and all angles in between. We can pass this light through a filter called a polarizer. So what a polarizer does is it's like a paper with a million different slits, if you will. So the light that is lined up with that slit will pass through it. And what we're left with is polarized light. So this light is only vertically polarized. So take a second, if you need to pause the video, take a look at how we go from unpolarized to polarized. We just pass it through a filter that has a bunch of slits, and the light that can fit through the slits we then say is polarized. So that brings us to something called polarized sunglasses. So there are other ways that we can polarize light. When light bounces off of a surface of glass, or if it bounces off of water or asphalt or some nonmetals, that light tends to become polarized in a horizontal direction. So here we have sunlight hitting the water surface, and the reflected light off of that tends to be horizontally polarized. We call this glare, and it can be kind of annoying, especially if you're fishing. So what we do is we wear sunglasses made out of Polaroid film that only allows vertical polarized light through. It blocks the horizontal. And we call that anti-glare sunglasses. So what polarized sunglasses do is they block the horizontally polarized light. That's all they do. They're not really shaded, or, well, they're kind of shaded, but that's basically what they do. And they cut down on glare. The next thing I want to talk about are 3D movies. So when you look at an object, your two eyes are going to view the same object from two different angles. Your brain then uses this information to judge your distance to that object. As a fun experiment, close one eye and try to figure out how close you are to various objects. You should notice that it becomes significantly harder for you to tell how far away you are from certain things. So 3D movies then take advantage of this to trick your brain into thinking that you see seeing things that have depth. So to watch a 3D movie, you wear special glasses. And the most common of these are polarized glasses with two Polaroid filters that have different orientations. So the projected movie is actually two separate films, one for each eye. And it's the fact that we have these two images that give movies, or 3D movies, this depth. So one movie is filmed to be vertically polarized. The second movie is filmed to be horizontally polarized. And then you get these two different images coming at you at the same time. And again, it fools your brain into thinking that that movie has some depth, that you are actually viewing something that has a size to it. All right, that's going to conclude our unit on light.